Hello, everyone. This is the second talk of our seminars from the Master in Quantum Computing Technology of Universidad Politécnica de Madrid. On this talk, we have with us Iraitz Montalbán. Iraitz is a former student from the Master, from the previous edition, and he's going to deliver a talk on genuine multipartite entangled states focused on detection and quantification. And to provide you a bit of background about Iraitz, he holds a degree in computer engineering from the University of the Basque Country here in Spain, and has several master's degrees in fields as statistics and applied mathematics, data protection, and now quantum computing. He has more than a decade of experience in relevant roles in innovation projects and within the business environment, and also as a researcher linked to entities as the University of the Basque Country, where he studied, and the Basque Country for Applied Mathematics and Technalia. He's now working as head of innovation in SDG Group, and he also is teaching at the University of Deusto here in Spain, and collaborates with the Universidad Oberta de Catalunya. So I hope, Iraitz, I got it right. Please, otherwise correct me if I'm wrong. The talk will take around, if I'm right, 20, 30, maybe a bit more. And afterwards, we'll hold a small Q&A session. So you will be able to share your questions with Iraitz. If you have any other questions before that, feel free to share them in the chat, and we will try to address them if possible. So with that, Iraitz, all yours. Thank you for sharing your work with us, and all yours. Thank you.
Thank you so much for the introduction. You should be seeing my screen, right? So as you said, we were going to talk about genuine multipartite entangled states, detection and quantification. That was part of my master thesis. I did this thesis, and it was possible thanks to Nicolas Scarpa and Patricia Contreras Tejada, that were my supervisors, and they were patients. They had enough patience to teach me all those things, all those theoretical things that we're going to talk about. So this is the outline of the talk. I'm going to talk a little bit on the research scope, what we were focusing or what we were trying to achieve with this research. I'm going to talk specifically about entanglement and the type of entanglement we're going to cover in here, detection and quantification, the means we will have, and some of the entanglement monotones we used within our research, the implementation we provided, and some of the results, conclusions, and future research, right? So first of all, the idea of this research was trying to finding computationally efficient ways for detecting and quantifying genuine multipartite entangled states, right? Why is this? Because the motivation is key in here. Entanglement is a really a valuable resource. Is why quantum computation is the field is so interesting, and is one of these key features that we try to understand or better understand in order to use it in tasks like quantum cryptography, quantum teleportation, or quantum computation per se. Is what makes qubits interact between them, and it's one of these resources we need to treasure, right? So our contribution was studying entanglement at beyond the bipartite case, and researching for entanglement monotones and ways to detect and quantify the entanglement, the amount of entanglement in a given quantum state. In order to do that, we chose some interesting entanglement monotones and adapt them for the genuine multipartite entanglement case. And in order to provide this as a resource to the rest of the community, we focused on what were the tools we had at hand, finding QETLAB, one of these MATLAB toolboxes that was really handy for the bipartite case, and we tried to extend it to the genuine multipartite entangled scenario. So we did fork the repository, the QETLAB repository, and it is publicly available to all of you. Entanglement. Well, I think that most of you already have heard or know what entanglement is, but just in case, if we take the simplest scenario, the pure bipartite case, so we have two parties interacting and composing a single quantum state. If this quantum state can be written as the tensor product of the two underlying states, then this it's called a separable state. If this is not the case, we can consider the state to be entangled. And basically, the most known examples for the bipartite, pure bipartite entangled states are the Bell states. So we know that, or if we look at these states, we see that we cannot write them as tensor products of each of the qubits that are compose the system as a whole, right? So we can only take it as it is. If we move forward to the multipartite scenario, so more than two parties, this gets a little bit more complicated, right? You could take all the n particles and tensor product them. If you can do that, and the outcome of this tensor product is your state, so you can describe it as it is shown in the picture, then the state is called fully separable. We are okay with that. If that's not the case, but you can find a group, let's say a group of particles n and its complementary m bar, and compose two states that when you tensor product, you obtain your quantum state, the state you have at hand, then the state is called biseparable. You have found a cut on your n parties, so you can divide it, let's say, in two, and by tensor product in these two states, you conform your quantum state. So this state is called biseparable. If that's not the case, if there is no bipartition you can find within your state space that describes the state you have at hand, then it must be genuine multipartite entangled state, right? There is no bipartition that will allow you to write it like you see in the picture and obtain the state you have at hand. A simple example of this are the W state or the GHC state, states that have been covered in the literature for a while now. And we do know that these are genuine multipartite states. These are the tripartite examples of a genuine multipartite state. Sorry, genuine multipartite entangled state. So as you see, there is no way where you can come with a solution where tensor product in these subsystems, you will end up with the same state, with this result. So that's what we are looking for. That's our aim, and we try to cover all those states that have this specific composition, right? This regarding the pure states, but quantum states often and in particular, when you try to build them in the laboratory, you won't have the luxury of having pure states at hand, and probably you will have to work with mixed states. So for the mixed state scenario, we understand a mixed state as the convex combination of pure states, and we can extend what we have seen before. And if a mixed state can be written as the convex combination of fully separable states, fully separable pure states, then the mixed state will be considered fully separable mixed state. If the state can be written as the convex combination of biseparable states, pure biseparable states, then the mixed state must be biseparable. And otherwise, it must be a genuine multipartite entangled mixed state. So that's the description, the taxonomy of entanglement we will be working with. And from there, we wanted to see what are the means we have in order to detect and quantify those states. So if I'm given a tripartite, a multipartite state, I want to have efficient means to detect if it's entangled or not and how entangled it is, right? So the first examples we have in the literature trying to do this, we owe the PPT criterion to Perez and Horodecki, that based on the partial transposition of a density operator, they were able to find a way in which we could somehow detect an entangled state. In this case, if we do the partial transposition of our density operator and it has negative eigenvalues, we can see that the PPT state space is surrounding the separable convex space. So if the partial transposition has negative eigenvalues, that means that we are outside this space. Then therefore the state we have at hand is entangled, right? It's a way in which we can detect an entangled state. It doesn't have to be for all, or it is not the case for all entangled states, but for some entangled states, if we do the partial transposition and we obtain a negative eigenvalue, then the state must be entangled, right? This is simple enough for the bipartite scenario. A different approach is obtaining an entangled witness, which is a special type of operator. This operator, when you trace it over a separable state, will return a positive value. And actually, this witness operator is or has tracing all separable states will always return a positive value, except for the raw entangled state we have at hand. So somehow this W density operator cuts the space in two, where we can put all separable state at one end of this cut and have our entangled state on the other. So it's a simple way to have an operator that will detect our entangled state. The problem is that when we move to the multipartite scenario, things get, as we talked before, things get a little bit more complicated. And don't take it as the picture as it is, because in order to visualize it, we will need a volume, in this case for the tripartite scenario, but somehow it helps us envision what are the challenges we find here. So we have the fully separable, the set of fully separable states in this convex shape in the middle with the FS label in it. Then for all bipartitions, if we cut the three spaces or the three, we do different bipartitions on the three spaces we do have, we can find these ellipses that are the shape of the biseparable states. In between those biseparable states, and you have to think about it as a volume, we find the mixed biseparable states. So mixed states that are a combination of biseparable states. And outside this space, this convex space, we find our entangled states on different classes. We have the GHC family, we have W family. Don't see it as an overlap. So don't see it as W class is inside the GHC class. It's not the case, but you have to understand that outside this convex shape in the middle, we find these entanglement states. And what we need to do is try to find the boundary that will help us detect when a state is outside this shape, so it is entangled, and we can quantify somehow its entanglement. So in order to do that, one of the first work we went through was the paper by Junich et al., where they described the PPT mixtures. As happened with the PPT criterion of Perez and Horodecki, this is an extension of this criterion, and it allows us to describe a shape that contains all these biseparable and mixed biseparable and fully separable states. So PPT mixtures are convex combination of PPT states on, in this case, the three different cuts we have on a tripartite scenario. And the thing is that no genuine multipartite entangled state can be described as such. So if we don't find any combination that will end up into our state, then our state must be genuine multipartite entangled. But the thing is that for these cases, we can find a decomposable witness W that is applies to all M bipartitions of our space state at hand. So by finding this witness operator, we can find a way in which we can detect our state as our entangled state, right? And actually, they propose by means of this optimization problem, they propose a way in which we can construct this witness operator. So by minimizing the trace over this witness operator and our raw state, subject to all bipartitions where W needs to be this decomposable witness, we can find our witness operator. And actually, if we take this cost function, it happens to be the negativity, or it acquires the same value as the negativity for the bipartite case, but we can extend it to the tripartite and multipartite scenario. So we extended the name of the negativity for this entanglement monotone. That is no other thing that an entanglement monotone in this case is no other thing than a mapping between a quantum state and a value. This value will be 0 when the state is separable, and you will be positive up to a maximum where the maximally entangled state is. So it's a way in which we can quantify how entangled our quantum state is. Trying to find different approaches for this, we also went through this paper by Wei et al. In 2003, that they proposed a different approach based on the overlap between a given entangled state and the closest separable state, right? So thanks to this, if you have an entangled state at hand and you can find the closest separable state, you can measure somehow the overlap between these two, and it works as a distance. So depending on how close we are to the closest separable state, that marks somehow how entangled the state is. The good thing, or it could be hard to find this lambda max, but Zhang et al. In 2020, they proposed a method that allows us to approximate this lambda max by the fidelity. The problem with this method is that it only works for bipartite states and some certain higher dimensional states, which we don't know beforehand, right? So we need to find what are the cases, the specific cases where this fidelity can be used in order to measure this entanglement, to have this entanglement monotone. And actually, based on our previous work by Watrous in 2012, they proposed a solution to approximate such fidelity. And lucky for us, it's an optimization problem of similar characteristics to the previous one. So by solving this optimization problem, we can find the fidelity between rho and sigma. If rho is our state and we want to identify where is the closest separable state, we just have to go through all separable states, sigma in this case, and find their distance. By minimizing these, we find the minimum distance between the two, which is equal to the fidelity in this case. So we do have two entanglement monotones, and given that negativity, the method to construct the negativity entanglement monotone provides us with a witness operator, we try to also find a witness operator that was accessible for the other the other entanglement monotone, which in this case is the approximation to the geometric measure of an entanglement. And actually they proposed constructing it by using the fidelity, as you see there. We used that method, even though that method only is valid for pure states and can be valid for some mixed states. So we needed to identify when this witness operator was a valid operator detecting the entangled state at hand as well. So these were our two methods. These are the ones we chose to implement and test against the theoretical results. And this is what we did within this work. For the implementation, given that QETLAB uses CVX for convex optimization, for solving convex optimization problems, and we had not only convex optimization problems, but semi-definite programming problems, let's say, we used that implementation. Semi-definite programming, it's a subclass, it's a subfamily of convex optimization problems that describe an optimization problem that has a convex function as the cost function. And actually, it is subject to a set of symmetric matrices that describe a cone in which we need to optimize. The good thing about this type of problems is that once you find the solution, you are guaranteed to be a global optima. So once you have the solution, you know that there is no better solution than that. And that's what we did. We took CVX, that was the default library within QETLAB, and we implemented these two entanglement monotones and optimization problems, right? So if you see, the code resembles a lot what we have described in the previous sections. This is the code for computing the negativity, the negativity and the density operator, sorry, the witness operator related to that. That basically describes the variable W, that's the witness operator we need to construct. All the P density operators that we will use for the decomposable witness, and minimize the trace of rho and W, the product between rho and W, subject to all bipartitions meeting the previous requirements we specified, right? Also, for the approximation to the geometric measure of entanglement, we find a similar thing. The only difference with respect to the theoretical work is that we need to provide separable states. And as we have seen before, finding if a state is separable or is entangled could be complicated. Actually, this would render in a nested optimization problem that we don't want to go through, given the resources it would require to be solved. So we did a simplification of the problem, and you will see what that supposed for the results we will see below. In this case, we took a separable state as the partial transpose, as the one that has a positive partial transpose, so a PPT state in this case, right? So that means that we are not covering the green triangle that was the space for the mixed biseparable states. We won't be able to detect those separable states that are within this region, and this means that we will have some discrepancies when we work with highly mixed entangled states. You will see that in the results below. And well, from there, once the optimization problem is solved, we compute the fidelity, and of course we add a warning when the trace of rho to the power of 2 is below the fidelity to the power of 2, because we know that we won't be able to detect those states with the witness constructed by the method described in the paper. So once we had these two implementations, we needed to test against the results, the theoretical results, and the results in the state of the art. So basically, we found consistent results with the theoretical ones regarding the Bell state scenario, so the pure bipartite case. Even tensor addition and subsystems, the entanglement did not vary, and the results were equally valid. Tripartite states and multipartite states, we also tried with some Dyke family states of 4 parties, and the results were equal. The numerical results up to a resolution were equal to the theoretical ones, except for one odd case, that was the W, the tripartite W state, that we got some numerical discrepancies between the theoretical negativity and the obtained value by this optimization problem. So this is the only case from all the cases we tested where the theoretical and the numerical result wasn't equally, wasn't as close as the rest up to a numerical resolution. But from the pure case, we started messing around with the mixed states, and we took some of the examples already presented in the papers. So by Wei et al., we took this state that mixes between W and the complementary of W state, tuning it by this P parameter. So we see at the edges of the graphs, we see what happens when we only have like the pure state, and we obtain this value as the measure of entanglement. And when we start mixing the two, we see that the amount of entanglement goes under, but never below a certain value. So no matter how mixed the state is, when we work with these two pure genuine multipartite entangled states, the resulting mixed state is still a genuine multipartite entangled mixed state. So this is an interesting result. This is something really interesting that actually reflects what the same results they had in the original paper. One interesting thing as well is that, as we can see on the other graph, is that for the negativity, or the way in which we computed the negativity, the obtained witness operator was always valid, was always under this this zero value for the trace with the entangled state, but not for the case of the geometric measure of entanglement and the way we chose to construct witness operators. So when the state is too mixed, the obtained witness operator is not valid to detect this state. So this is something that we need to have in mind, that working with highly mixed states and using these type of constructions of witness operators could render in non-valid witness operators. Right? Also, we tried with different states, with two of the families that we know that are quite different one from the other, and actually the results are interesting, given that the way in which the entanglement monotone behaves when we get closer to one or the other end are a little bit different, right? So we get the same result for the GHC, the pure GHC state for both entanglement monotones, negativity and approximation of geometric measure of entanglement, but that's not the case on the other end when we apply it to the W family, or in this case, the tripartite W state. Of course, seems that the GHC family is a little bit more resilient to the mixture of with different states more than the W state, and that means that we can push it a little bit further in the left-hand side end, where the GHC family is by the description of the formula. So we also try to break the entanglement, because up to now we were working with pure entangled, generally multipartite entangled states, and the results of the mixed states weren't breaking the entanglement within the mixed state. So we took the example of isotropic states, and we tried to see if we could break it at the point where the theory says it should break. And actually, we see that both entanglement monotones were able to match the same result. So we know that for the maximally entangled bipartite case, we know that at 1/3 it should be no longer detected as entangled, and that's the case. You see, that's the point where the two entanglement monotones were unable to provide positive values, but the behavior of the two is quite different, right? The negativity has a linear shape up to the maximally entangled state, the pure maximally entangled state. And for the geometric measure of entanglement, we see that the approximation is exponential, and that the gradient, when you get closer to the separable state, it's quite it decreases a lot, which is something we would need to take into consideration for the rest of the results we will see. We took also an interesting table from the Unich et al. Paper, where basically the method we use is their method. So our numerical results should match those presented in the paper, and they did. But we tried to do this with the entanglement, with our approximation to the entanglement, the geometric measure of entanglement. And actually, that was the entanglement monotone. This geometric measure of entanglement, or our approximation, was actually telling us that we could go a little bit further, adding noise to the pure state. So the idea is that you could be adding up to 0.52 according to negativity noise to this pure state, and still not break the entanglement of this state, or the resulting state, if I should say. And actually, for the geometric measure of entanglement, this limit was up to almost 80%. So you could add 80% noise and 20% W tripartite state, and the resultant state will still be entangled at a measure, right? And we know that this is not true, because they proved within this paper, the Unich et al. Paper, they proved that if you go a little bit further than their limit, then negativity, the one that that says 52 for W tripartite case, we know that these states are already separable. So there is something going on with the geometric measure of entanglement, or our approximation of it. And the thing is that if you see for the W, the tripartite scenario of the W case, if you start adding noise to it, it's still entangled until at one point it says it's no longer entangled. That is the limit that they were describing at the paper. But if you take the geometric measure of entanglement, you see that it goes a little bit further. This problem is because we weren't able to detect the limit where you go into the mixed biseparable states. So we are actually detecting as entangled states that are probably mixed biseparable states. So this is the region where genuine multipartite entangle, the geometric measure of entanglement will provide a positive measure for states that are not genuine multipartite entangled states, right? So this is because of how we describe this limit by only taking into consideration the three ellipses, the three yellow ellipses of the pure biseparable states. So we know that there are some false positives when we work with highly mixed states, or at least states that are highly mixed with noise. Given that we could see the evolution of mixture of two states, we try to go a little bit further as well, and taking from Wei et al., we played with these three-state mixture states. And the funny thing is that even though the entanglement decreases in all scenarios, that the resulting combination of parameters does not give a pure state as a result. None of these states were never below the limit of 0, where your state would be separable. And you can see that the shape of these surfaces resembles the behavior we see with the geometric measure of entanglement and negativity. But it's interesting to see how the addition of each different family provides a different shape, a different way in which the state evolves. Of course, we try to do the same thing and break the entanglement, and by the addition of noise, in this case, for the W, a combination of W state, GHC state, and noise. And there is a limit where the entanglement was no longer detected by the negativity and still detected as genuine multipartite entangled state, but the approximation of geometric measure of entanglement. But we know that this is the region where we cannot trust our approximation to the geometric measure of entanglement. So these were quite interesting results. And it was also interesting to see that we can find methods in which we can build entangled states, genuine multipartite entangled states, and actually mixed states without losing this entanglement. We can find ways in which we can construct the states we want, maintaining their entanglement, right? So some of the conclusions for our work and future lines of work we would like to also work on is the need of clear separability criteria and computationally efficient means in multipartite scenarios. We saw that in particular for the approximation of geometric measure of entanglement, we need to properly describe the limit where separable and genuine multipartite entangled states. And when I mean separable, I mean the whole thing, the whole convex set of biseparable, mixed biseparable, and fully separable states. We need to find a clear separation between the two, so we can input that into our optimization problem in order to not run into these false positive measures. Identify entangled monotones that benefit a specific entangled genuine multipartite entangled states or state families. So we know that each entanglement monotone fits better to a given family, and it will be nice to have this matrix somehow where we can relate the best entanglement monotone for a given family of genuine multipartite entangled states. Thanks to that, we could contribute, we could elaborate a method where you could build different type of mixed genuine multipartite entangled states by tweaking and adding some family or a given family against a different family of general multipartite entangled state and build some custom general multipartite entangled states for you for a given purpose, right? And of course, we will need to improve the witness construction for the distance-based scenarios. In this case, the approximation of the general multipartite entangled state, because we know that for a highly mixed of pure states, there will be some issues there. Right? As this was this code was built on top of an existing library, QETLAB, that has a function that grabs all methods that could be used for a bipartite scenario that is called is separable, that tells you if the state is separable or not. We would like to add it to this code base so that by only calling to this function, you could have the plethora of methods you could find in order to detect and quantify a quantum state, no matter if it's biseparable or general multipartite entangled states. Sorry, bipartite or general multipartite entangled state. So we would like to wrap it up within this function, and in the future, probably we will be able to do that when we merge these two branches, the official QETLAB branch and our specific branch. And basically, that's the end of my talk. I will, when you have if you want, you can go through all the literature I referenced within my talk, and it's actually quite interesting to go through all of it, even though it can be exhausting. So thank you so much for your attention, and I hope you have at least one question.
Thank you, Iraitz. Thank you for your talk. So first of all, we are going to share the link for the next talk, so you can, any one of you can undergo the registration process. We will start that in 6 minutes, more or less. So if you have any questions, feel free to just unmute yourself and jump in, or you can put them in the chat. I can already see one by Aitor Moreno. Actually, maybe it's two. So he considered it very interesting. Thank you for that. And the practical application is only to ensure a more efficient measurement or to minimize the noise of current NISQ computers. And he has another one, but maybe we can leave that for later.
Well, even though our work was related to detecting and quantifying given states or multipartite states in our scenario, let's say the aim is finding a way in which you can use that for NISQ devices where you are working with different set of qubits, and you will end up with an entangled net of qubits. You could use this type of methods in order to know if you have broken the entanglement of your system or not. That's somehow the idea, is to validate that your state or the resultant state is still entangled in those complex scenarios where you have not only two qubits interacting, but many of them. The applications, well, once you start working with a network of qubits and you want to construct a complicated, let's say, this multipartite scenario of entangled state, this will be a way in which you can make efficient protocols, let's say, in order to know that you are doing what you expect you're doing, given that NISQ computers and the devices we do have nowadays are noisy, and you will probably add instead of, well, while thinking you're working with pure states, probably you will be working with mixed state that have some noise at some end. Hope that helps, Aitor.
Thanks. Actually, yeah, I think so. You answered the next question from Aitor, which was if there were other practical applications. So okay. That's great. Okay, is there any other question from anyone? We have a few minutes left. Okay.
Nobody? Not even Jaime. Wow.
I think he was there, yeah. Okay, so it seems that there are no questions for now. So thank you, Iraitz, really for your talk and the work you did on your master thesis. It was really interesting, and I hope to see you all next time. So thanks. We will be closing this session now, and I will be jumping to the next one. So thank you, everyone, for joining today.
Thank you, everyone.